Hello. Today I'll be going through problem 5.20 from the Ulaby textbook. This question is basically asking if you have a square loop with a current I1 running through it, and then you introduce on the same plane a long conductor line I2 with current I2, what is the force acting on the loop? And this is basically the force acting on the loop due to the new conductor that was added. So just to start, I'm going to write down our variables here. So we have A equal to 2 meters. We have I1 equal to 5 amps. And we have I2 equal to 10 amps. And our goal is to right? Okay, so the way we want to do this is we want to look at the forces on each section of the loop. So we want to look at 1, 2, 3, 4 separately. So we can start by determining the force on section 1 over here, this one. So I'm going to say F1 is equal to so the current of our long conductor times the length as a vector with the cross product of the magnetic field of our original loop, like just this side here. So we can treat that as just a straight wire. So let's plug in some values. So we can say it's I2, our length is just A, so I2A. Let's think about the direction. We can see it's pointing in the negative x hat direction, so I'll make that negative I2A x hat, and then cross producted with the magnetic field. The magnetic field of that one section of our loop. So we will use the equation for a wire magnetic field. So it's mu naught I, I1 divided by 2 pi r. And in this case, r is simply a over 2. And if we think about our right-hand rule, we can see that as we curl our hand up after going in the negative x hat direction, that we're actually kind of pointing up. So we have a z hat over here. So if we take the cross product here, we should arrive at y hat, and then just taking our variables, we have mu naught I1, I2A over 2 pi A over 2. Okay, then we can see that, force 3 or side 3, F3 is just same deal in the opposite direction. And we can actually see that, this is, I'll get another color. This is an attractive force for force 1, but for is side 3, it's a repulsive force because of currents. Am I mixing this up? I think, yeah, I guess this one should be a repulsive force actually, and this one should be an attractive force. No, sorry. No, this is a repulsive force, another one's an attractive force. The whole point is they're in the same direction. So actually, our F3 is equal to our F1. Moving on to F2, we can, before we do anything, just see that our, if we have our I2, our L vector is really just in the, what direction is it in? It's in the negative x hat direction. So, and then this is cross-producted with our magnetic field of a wire. So we have mu naught I1, and this is in the negative y hat direction. Over 2 pi a over 2. Well, the whole point here is that we have an x hat and a y hat. And since you're doing a cross product of x hat and y hat, it simply equals 0. So this will be the same deal for F4 as well. So really it's just F1 and F3 contributing to the force. So we can say our force is equal to F1 plus F3, which is equal to y hat 2 mu naught. I1 is 5 amps, I2 is 10 amps. And then we have our A, which is 2 over 2 pi times A over 2 is 1. And we know mu naught is 4 pi times 10 to the negative 7th. And if we compute this out, it'll equal y hat 4 times 10 to the negative 5th newtons. Okay, I hope this helps. Thanks for watching.